German scientist Heinrich Hertz experimented by shining lights on electrical circuits, and results seemed to confirm Maxwell's theory. Our knowledge is complete, said Hertz. A refutation of these views is unthinkable. The wave theory of light is a certainty. However, Hertz's assistant, Philipp Lenard, decided to look more closely at one of the experiments where there was a gap in the electrical circuit.
Different colors across the gap. Right now there's no high voltage, so you don't see anything happening. Let's go ahead and fire up the high voltage.
Okay.
Lenard found that if he shone light at low frequencies, red, green or blue, on these two metal balls, nothing happened. But if the light was above a certain frequency, into the ultraviolet, electrons escaped from the metal and jumped across the gap, completing the circuit and creating a spark. Now that didn't sound like the action of a wave.
Now, this doesn't make any sense, a threshold, a sudden change going from violet to ultraviolet, if light is a wave, smooth and continuous in how it delivers its energy. But if light is a particle, a threshold makes a lot more sense.
Here was an incredible paradox, because so many experiments could apparently only be explained by the wave theory, but here there was this new class of experiments that could very easily be explained by particle theory, but not by the wave theory. What to do with this?
No one could have predicted the problem would be solved by a patent office clerk in Switzerland. But that's what Albert Einstein was when he came up with the answer. In 1905, Einstein had the revolutionary insight that light has a dual nature. In some contexts, as Maxwell and Hertz had shown, it was a wave. But in others, as in Lenard's measurements, it consisted of discrete quanta of energy, or photons. The higher the frequency, the greater their energy. Amazingly, Newton and Huygens had both been correct. An experiment using modern equipment at Stanford shows very clearly that Einstein was right.
What we want to do is we want to observe single photons. So what we have here is we have a very sensitive photodetector, and it's connected to these optics through this fiber optic cable, which basically just funnels light into the detector. So we actually need to cover up these optics, and we need to actually shut the room lights off. And I'll use this flashlight as a light source to get photons into the detector.
In darkness, you hear no evidence of photons striking the detector. As the light becomes stronger, you hear a growing rush of photons. When the light is dimmed, there are fewer and fewer photons reaching the detector until you begin to hear the photons one by one.
So this shows that Einstein was right, and light is indeed made up of particles.
But nobody else could understand how light could be both a wave and a particle. Not even the famous physicist Max Planck.
We know today the letter that Max Planck wrote to recommend Einstein. And in this letter he says many complimentary things about Einstein. And then he comes to Einstein's theory of the photon, and he says, you should forgive Einstein. Even a very great man can make a big mistake occasionally. And of course, eventually Einstein got his Nobel Prize for that work.
It wasn't relativity that won him his Nobel Prize, it was what he called the photoelectric effect.
The photoelectric effect is really the stroke of genius. It took courage, of course, also took insight and this genius touch. As I emphasize again, that transcends simple analysis and mere logic. And that is what is truly great about this great mind.
The entire history and development of modern work on solar electricity depends on Einstein's understanding of this photoelectric effect. In this context, light consists of lots of individual packets of energy, ready to react with whatever they strike. Einstein's insight that set the stage for the future advent of solar power. In the mid-20th century, some of the greatest developments in applied technology were made at Bell Labs, the Bell Telephone Laboratories in New Jersey. Here, in 1947, William Shockley, John Bardeen, and others developed the transistor, the most important electronic discovery of the century. It was both a switch and an amplifier, and it transformed everything from telephones to computing.
It revolutionized everything. You can really speak of the world before the transistor and the world after the transistor.
Dr. Walter Cohn worked here as a young man in the 1950s.
Well, the first time I came to Bell Labs, it felt like a very intimidating place. It was known to everybody in physics as the #1 laboratory in the world. My recollection is that there were approximately 3,000 people working here. You know, everybody was doing his thing, but everybody was connected to other people who were doing their things.
It was this connection that brought together the work of 3 scientists to create the world's first practical solar cell.
Here are the inventors of the Bell Solar Battery.
Darrell Chapin was an electrical engineer. He'd been experimenting with early selenium cells for powering telephone lines in remote areas. A physicist, Gerald Pearson, was trying to develop a rectifier to replace mechanical telephone switching devices. And a chemist, Calvin Fuller, was working with the semiconductor silicon as part of the transistor project. Bell scientists liked silicon because of its electronic characteristics and because it was abundant. It's basically sand and makes up more than 1/4 of the Earth's surface. A single atom of silicon has 4 active electrons, which are called valence electrons. In a crystal of silicon, each of these valence electrons, together with a valence electron of a neighboring silicon atom, forms a bond joining those 2 atoms. However perfect it looks, solid silicon, like all semiconductors, doesn't work electronically unless a small fraction of the silicon atoms are replaced by foreign atoms called impurities.
Pure silicon is one of the dullest substances you could imagine. Does very little of interest. You introduce these minuscule fractions of impurities, and I say minuscule, part in a million, part in a billion atoms. Suddenly, all kinds of exciting things can be made to happen.